Okay, now we'd like to continue our topics on limit. Uh, yesterday we discussed that the limit is a concept that is um, visually we can see that uh, the uh, the concept of getting close to, and when we talk on how we apply it in a physics problem here. This is from Galileo Galilei experiment. From his observations, he observed that we have correlations between the positions and time, in which it's correlate to 4.9 t squared. And we apply that formulations to calculate the average velocity, and then from the value, we play along with those value and then try to get the uh, smaller interval, So first we get the interval 0.1 seconds, and then we make it smaller and smaller, and then we kind of proving that when we take the interval as small as possible, we are ended up with something that is going to approach some value that is probably we calculated, and maybe you can also calculate. Okay, thank you. Calculate and get the number 49. So maybe I will add this. So as t approaching 0 probably, right? Or maybe delta t to make sure that you know that this means the interval. Okay. Then the value, or let's say the v is getting close to 49. Okay? And this is actually what we are going to deal with in limit. Okay? So this is to say that when we limit the interval of time, in our case is our variable, okay? And when we limit that getting close to 0, if the velocity or the average velocity will be getting 49. And then we can also say this to define what we have as instantaneous velocity. Okay? So we can define the instantaneous velocity as a limit of the interval of time getting closer to 0 for the average velocity. Okay? Or in general, let's go back to what we have in here, that the tangent line is actually our secant line when we limit those secant line for as x approaching some point, okay? Approaching some point that is on the point on the tangent line, which is point P. Okay? This is point P. So our goal is actually start from the blue line. We want to make this blue line getting closer to the tangent line. So we can have some definition. So we have, or we can use this concept of limit to define our tangent. Okay? So let me write in a new page here to give you more concise and maybe precise definition. Not precise definition, but maybe intuitive definitions. That is, let me check here. So let's see this graph here. Okay. When we have this equations, or we have this functions, x minus 1 over x squared minus 1. Okay. So we draw, and then you need to observe at the denominator, at this x squared minus 1. Okay. We need to be careful that we need to define this in the domain, okay, in their domain. Okay. So that's why when we look at the graphs, we usually, when we draw manually in your paper, we usually write this, having some open dots like that. Okay, it means that it's not defined on that point. Okay, but perhaps you try to draw in graphic calculators or websites, if you draw in those software, sometimes this phenomenon is not really appear. What you need to do is you need to zoom in, because I think I already mentioned it yesterday, because of the limitation of pixels and resolution. Okay. So when you deal with this some software and you want to prove, oh, there is some hole. Okay, so there is some hole. There's some hole here. Of course, when you draw with your hand, you can just draw like hole. Okay, but proportionally, if you think precisely, the hole is actually just a dot. So if you see with your naked eye, it won't really, you cannot really see, okay? Unless you try to zoom in, and you will see something weird going on. Okay, maybe later we can show if we have time. Let me just show just using GeoGebra, and then we are going to see that there will be something weird happen on those points. Okay, so this going to be our definition. So we can write, okay, if we want to write with limit, we can write limit this approaching, okay, this is approaching this x equal 1, right? So we want to approach how is the limit at this x equal 1, but at the same time, when we put x equal 1, it's not defined, right? But because we know the concept of limit, which is we can ignore the small gap, we can write the limit as x approaching 1 for this function x minus 1 over x squared minus 1. This will be equal to, when we look on the graphs, it seems it's approaching 0.5. It seems it's approaching 0.5. So we can write this. Okay. Although, remember, when we talk about limit, the numbers, the real numbers or the exact numbers is not like we did here. Okay? We have like small gap. Probably we can say that from the right side, maybe this will be 0.000001 or 9 or 1. Okay, and from the left, maybe here, let me just this is just illustration, okay, to see what kind of actually we have here. So probably it's 0.9999 on the left. Okay, but with limit concept, we can say that it seems it's approaching some value 0.5. Maybe 0.5 around here is 0.49999, or maybe here it's maybe 0.500001. Okay. So all things here to see that there is like a really small gaps, and it seems that with the limit concept we can ignore that small gap, so that we can write the limit is 0.5. Well, we can actually, if you want, you can try to check. Okay, you can try to check using some x. Maybe start from 0.1, 0.01, 0.001, and then maybe from 0 you can start maybe 0.9, 0.99, 0.999, and you will see some patterns, and it will approaching some number that is, when you take it with the small gap, you will see that it will going to approach 0.5. Okay. Okay, now from this visual, from this graph, we can write, we can say the definitions. It's called the intuitive definitions. Intuitive definition of limit. Intuitive means we are not exactly know how small the gap is. We just say, okay, it has a small gap, and when x approaching like really small gap, small interval, the function also going to approach some value. We're just saying that. We are not sure how small it is, or in any way in mathematical notation, we are not sure how small that is. Okay, so we can just say that suppose the functions define when x is, now the keywords is near, okay, near number, let's say just a, just to say it in general. So we can write, if we have limit as x approaching a of some functions, this will going to be some L, some value L. Or this is, we can write limit, or the limit of functions f of x as x approaches a equals L. Okay, now near, okay, let me just explain what near means. Okay, so near, it might be in open interval that contains a, but maybe not a, like we did here. There is a hole, it's the number 1 is not included there. Okay, but if we can count the limit, we can compute the limit. Okay, because what we are going to measure is just the near number a, okay? The near number a, not necessarily to be the a itself, but a can be also included. Well, it depends on the functions, right? It depends on functions. But in our case here, if for this case, if when we put a, it becomes undefined, as long as we can compute the limit, we can measure the near number within the a, then we can compute the limit. Okay. Okay, let me give you another okay. Now from these definitions, we can arrive at least some possibilities for the graph. Okay, so let's say we have a random functions for these three random functions here. The first one is just a regular graphs, continuous. It doesn't really have anything to worry about. Okay, and there's no hole whatsoever, right? There's no undefined points. So we can say that we can find the limit easily. Okay, so as x approaching a, the limit will be L. Okay. And the second one is the same with the example at the very beginning. So there is a hole, but it seems when we deal with the limit, we can go here, as long as we approaching this a, because that is what we are going to compute. We see that it will approaching L, so it's also, we can compute the limit, right? No problem. And we can also have this kind of graph or condition. Okay? So what this means, okay? So you see that there is the dot, full dot here, the black, full dot. But then you have also hole. So this is hole. But this is also another defined point. So what does it say? Let me just add some value here. Let's say this is value p. Okay. If this is f of x, this means when we plug in a to the function, this will be equal p. Okay? But if we take the limit as x approaching a of the function f of x, what is the value? L. Okay? It's L. So this is also can happen. So when you plug in your value, your x, perhaps that will be another value that is outside of the curve. It can happen. But when you deal with the limit, you will get the L. Okay, so this is also can happen. Okay, it also can happen. So all these three, they are all we can compute with limit. Okay, when we compute with limit, it's L. Okay? But the condition is like the last part. When you plug into your functions, it's different from L. Okay? It can happen. It can happen. Okay? Okay. Now maybe before I'm continuing this part with another cases, to give you more ideas. Okay. Let me draw something here. Let me draw here. Let me draw a circle. And draw a triangle. Okay. Let's say I have point A, B, and O. Okay. And let's take if I have this as height of the triangle there, and then if we have this red line or red dash here is the radius of the circle. Okay, so R radius of the circle. Okay. So let's say we have a conditions. Okay, so we have a circle, we have a triangle inside. But let's imagine this triangle. It has three sides, right? Let's say we call it polygons. Okay, let's make these sides increasing. Okay, increasing the size. So this is let's say this n is the sides. It's 3. We can make it 4. We can make it 5, which means that the sides will be like this and then like this, but they still inside the circle. Okay, so let's imagine increasing. Maybe let me just go and draw the 6th one. The 6 is it's really bad. Let's say this is the hexagon. Okay, I think it's okay. I think that's better. Okay, and then same thing. We'll try to have this dash to note that this is the R. Okay, and then similarly, we can see the triangle. Okay, let's say A, B, and O, and let's just take this dashed line here as the height of the triangle. Okay, okay, so for the three sides, okay, if I want to find the area of the triangle, okay, area of triangle, the computations will be half, and then the base, which is AB, right, and then multiply with the height. Okay. Okay, let's say this is our triangle. Now we have this area of triangle. Now the same thing is happening here, right? This small triangle, but we now have 6 triangle. Okay, 6 triangle. Or if we take the size is n, our area here is half AB H. Let's just say n. Okay, n can be 6, 7, 8, depends on how many sides we have. Okay. So the key here is we can increase this n as many as we want. Okay. Now imagine if this is the blue is height, the h, the red is r. Okay. Imagine when you increase the sides. Okay. Maybe n equals 7, n equals 8, n equals 9, n equals 10. What will happen with the height and r? Getting closer, right? Getting closer. Okay, we can also deal with limit. Okay, we can also deal with limit. Okay, so imagine that when n is, let me just write increasing. Okay, increasing. I didn't say how many, but just say it's increasing. Then we can see that the height is getting closer to r. Okay. So from this area, we can say that limit as h getting closer to r is half a, b, let's write n first and then h. Okay. Okay. Now suppose that, okay, suppose here, suppose when n is increasing, okay, when n is increasing, the sides of polygon will be getting closer to the circle circumference, right? Which is equal to, let's say, 2 pi r. Okay. This is just to show you that we can also getting something here. So limit sh getting closer to r. So this is the sides of polygon. Okay, this is the sides. And then how many is it, right? So this will be equal to the circle circumference. So we can write down this is going to be 2 pi or half 2 pi r and then h. And then as h is getting closer to r, we are going to get our circle. Okay. This is also the similar method we can also apply for other case as well. Where you want to define some geometry, you define some area, some volume. Okay, we can also apply this concept of limit. Okay, so we can see that from the polygon, when we make the sides as many as possible, maybe you can imagine in your mind that it's going to be like a circle, right? Like a circle. Okay? But because this is limit, but perhaps it's not really smooth circle. Maybe there has like really small gaps. Okay, maybe it's not really smooth. Okay, but that's its limit. Okay, so it's really helpful to um, to apply limit with many cases, okay? Especially for engineering fields. That will be very important. Okay? And this additional informations. Okay. Especially limits is really helpful when we do some approximations. Okay? Some approximations. Okay. Okay. Now, uh, let me give you some limit here. Limit as x approaching 0, sine x over x is equal 1. How do we know that this, or maybe how do we know this equal 1? Okay. How? This is the graph. Okay, the graph. This is the first reason. How do we know this is equal 1? From the graph. That is the first thing. Okay, the first thing that we can do. We can graph, and then we can see that it's approaching 1. Okay, what method that we can compute? Anyone? Anything to say? How to compute this limit? Usually every year there will be some students that will be answering this with some certain answer. It seems correct, but not really correct. I just want to know. How do we know that this is equal 1? Mm-hmm. Circle? Yeah, circle. Mm, not really, not really. Okay, probably some of you familiar with the Lobital rule? Familiar? No? Lobital rule? Lopital? No? Oh, good. No? But this is not how it going works, okay? Lobital rule is another way, but it seems it's going to work with this way, with this method. Lobital rule is saying that when you have the limit, when you put the limit with you put the x inside the limit, you put 0, sine x is 0, x is 0, so 0 divided by 0, right? So 0 over 0. So whenever you find 0 over 0, infinity over infinity, what you can do is you are going to derive the top one, and then you're going to derive the bottom one. And then you put 0 again, and that will be your answer. That is L'Hopital rule. But we will learn that later, okay, chapter 6. But that is my summary, really fast summary, a really quick summary. But what will happen here when we have the sine x over x? If we derive sine, it will be cosine. X is just 1. Cosine 0 is 1. It seems okay, right? But that is not correct. Okay? That is not correct. That is not correct. The reasons is because of what we call the so if we try here, this is not correct because of circular reasoning. Okay. We will discuss this more later when we talk about derivatives. So I will keep this for now. Okay, we will go back to here later. Okay, when we deal with derivatives. Okay, and I will tell you what circular reasoning means. Okay, circular means it's going forward and backwards. So not really having any fundamental definition. So you are going to use definition that is going to be described by another formula that it's supposed to be here. So it's going forward and backward, so it's not really helpful. Okay. So I will tell you later about that. Okay. Anyway, so we will get this will be to be continued. Okay. Okay, let me check. Okay. Another point that is important in limit is we call the one-sided or one-side limit. Okay, one-side limit. Okay. As an example, we can see an example in we call the Heaviside function. It's a function that is applied usually for electrical components or in electrical engineering in general. How the functions will look like is you will have a line here and you have an open here. Sorry, an open here, and you have a closed hole. And this is 1. This is y, x. Okay. And this is 0. So this is just as horizontal line. But what's so important about this function is when you see this 0 and 1, can you think this 0 and 1 as a switch on your on-off button? This is how it works. Okay. So that's why it's used on the electrical device or electrical engineering in general. Okay. So this is to say that when we have this, that the functions defined by ht is defined as a piecewise of 0 and 1, and it will be defined with 0 as its restrictions. And Heaviside is the person, okay, the person name. The name is Oliver Heaviside. So it's to describe the electrical current when it's switched on and off at t equals 0. So to describe what happened in this t equals 0, we can describe with limit. Limit, okay, as t approach 0. But when we take the limit for this 0, we see that we have from the left and from the right with the different value. Okay. So we can try to make the limit from two sides. Okay. So first is from the left. We can write from the left with the symbols negative like that. This means that the limit approaching approaching to 0 from the left. Okay? This is how it described. Okay? So this is going to be 0. Okay? From the left. Okay? From the left. From the left is from here, right? And then another limit is from the right, from there. So this is limit as t approach 0 from the right. Okay? And this will be equal to 1. So we call this one-side limit. Okay? Example of one-side limit. We will discuss what is the consequence of this one-side limit. And remember, you will see this one-side limit, the Heaviside functions, more and more, at least next year. At least next year. If you take the engineering of math, you will see this again. Okay. Okay. Now the definitions. Let me just copy from the books. Yeah. Okay. The idea is actually the same as the previous limit. We are just seeing from each side, from the left side and from the right side. Okay? Depends on where does it, where it's going. Okay? Where it's going. For example, the left-hand limit. Okay, it is to say that as x approaching a, okay, the limit of a function of x will be equal to L. Okay? And the same thing with the right-hand limit. This is when you approach from the right side. Okay? From the right side. So x approaching a from the right, and then the limit of the functions will be equal to L. Okay, and then what's so important on what for this two kind of limit, okay? One side limit, left hand limit and right hand limit. What's so important about this limit? The first thing, okay, what's so important here is if we are looking at the previous limit here, let's just go back to the first example. We are approaching from the left, we are approaching from the right, and it seems the same value. It seems the same value, right? And then we can just conclude, oh, the limit will be, yeah, the L, or in this case, 0.5. But when we have this Heaviside here, one side is 0, one side is 1. What's the limit? The total limit, the limit as x approaching 0. 0.5. 0.5. Yeah, this one. How do you know it's 0.5? Because but there is nothing 0.5. Yes, correct. So we can say the limit doesn't exist. Okay? Okay. So I think I will go to the next page. So the limit as x approaching a of the function of x, this will be equal L, okay, if and only if limit from the left is equal L and limit from the right is also equal to L. Or if you want to write in more general way, this should be equal with this And then we can say that this so whenever you find different value from the left and right, then we can say the limit doesn't exist. Okay. Let me write here to make sure that you understand. So if limit is not equal, then limit doesn't exist. Usually, I'm usually write just T and E, which means this doesn't exist, does not exist. Okay, and then how the limit fail to exist? There will be several ways. One way is this one. The left hand is not equal to the right hand. Another way I will discuss after this. Okay? So when you compute the limit, make sure you see carefully whether it's the total limit or only from the left or from the right. Okay. Okay. Now how limit fail to exist? First example, limit as x approaching 0 of sine pi over x. Okay. If we look at this sine pi over x, well, we can try. Okay. We have the limit. We can try to check the x. Okay. Check x equal 1. Check x equal. So let's say we have f of x. Let's say we have this function, and we try for several x. For example, f1. This is sine pi. It's 0. If you try another number as well, and we see that when we have x is reciprocal of the 2 pi, 3 pi, like for example, we say the half, and this becomes 2 pi, and then it's 0, and it seems that probably it's 0, but we are not sure. But hey, we can draw this graph, right? So let's try to draw. Open. Say sine pi over x. Okay. Now what's happened here? Okay. We need to find the limit as x approaching to 0. 0 is in the middle here, right? But what will happen when we zoom in? So if we look from the left, okay, it goes up, down, up, down, up, down, and every time it's getting close to 0, the distance is getting closer and closer between the amplitude, right? Between the amplitude, it's getting closer and closer. Okay? The same thing happened from the right. When we getting close and close and close, and we try. I'm not sure how the depth and the resolution, but it seems that it's getting really green here, right? Really green. It seems like it's getting like when you try to use your pencil, it's getting like wow, right? So this is to say that when we have these situations, it means that it's not sure whether it's going up or down at this 0.0, right? So we are not sure. So at this point, because of the oscillations, the limit doesn't exist. So let me go back here, or let me put the screenshot. Let me edit this first, just to show you that this is we have done here. Okay, so we put here is to prove that we already draw the graph, and it has some oscillation here. Oscillations as x approaching 0. So not sure that whether it's going to 1 or -1. It's not sure. So we can say the limit doesn't exist. But the easiest way to see the limit exists or not is just if you can graph, try to graph. Another way for the limit to be not exist is this. Okay. Now, of course, from the picture we see that the same thing as x approaching 0. Okay, let me go through here. From the right, it's going up. Okay, from the left, it's also going up. To check, to confirm this intuitive graphs, we can check with some numbers for x, and we are going to see that as the x is getting smaller, it's getting really, really large, right? Okay, we will have break for 6 or 7 minutes. Okay, we will continue after a while. Okay, welcome back to reality. All right. Okay. Now we have this. Okay. 1 over x squared. Okay, 1 over x squared. So we move from the left, approaching 0, and we are going to see that it's going really, really high. Going to the right from the right side is also the same. Okay. But what we can tell you here is that whenever point that we plug in into 1 over x squared is going to be, when it's approaching 0, it's going to be really, really large. For example, you can just try x maybe 0.1 or x 0. Let's say 0.001. The more it closer to 0, you will get really, really high number. So this is to say that because of this phenomenon in our 1f x squared graphs, we can say that this is going to be, we can also write this as with infinity symbol. But of course, if you are going to, if you are asked whether this is the limit exists or not, the answer is it's not exist. Okay. So the limit doesn't exist. Limit doesn't exist. But then sometimes your mind's struggling. Okay. Oh, but this is infinity. Limit is infinity. But here's the deal. Okay, the infinity symbols, it means that um, it is a concept or idea, not a number. Okay, although it describes really large amount of numbers, but it doesn't really exactly say it's a number. It's just an idea that when you have it, means that it will be really, really huge amount, and you will not be able to restrict how much is it. Okay, that's the idea of infinity, and that's why we use the definitive symbols, infinite symbols. So we can say that when we have this limit as x approaching maybe some a and of the function of f of x, and when we say this is equal to infinity, this means that the limit increasing without a bound as x closer to a. And we can call this also with the terms infinite limit. Infinite limit. So you can say the limit doesn't exist, or in this case, this one here, the infinite limit, you can write the infinite symbol. And again, it's not that this is a number, it's not a number, okay? Or so when we write limit as x approaching a of f of x equal infinity, it means that this is just to say that this is what we call infinite limit. Okay? So let's define this phenomenon. So let f be a function defined on both sides of A, which means from the left and from the right, okay? Except possibly at A itself. This means that it can be a whole, but still we can count that. Then we have limit to infinity. So this means then value of f of x of f can be large as we want by taking x closer to A but not equal A. Okay, that is what we have done from the previous example. And the phenomenon for this infinite limit is at x equal A, or before when we have 1 over x squared, when x equals 0, we are going to have an asymptote. And that's the idea, okay, for this infinite limit. So we can also have vertical asymptote. I think I have the graph. So we are going to have an asymptote. Another way to describe this infinite limit, of course, if we have the negative infinite, it can also happen. So when we have the function here, when we try to getting closer to x equal A from the right, from the left, it's getting negatively large, okay, negatively large, okay. So this is to say that we can make this as, so the first one is just a usual, but the second one is having negative infinity. Okay. The definition is the same, but the difference is the other one is getting larger, but in negative way. So it's going down. Okay. So whenever we have this, okay, And of course, we need to also have the one side version. We can also have, so we can maybe only the left side from the left side. So maybe we can write this one here, limit as x approaching a from the left. This is also that. Or maybe here on the right. And right here we can write limit as x approaching a from the right. But it's going to be negative. So from all the combination that you can make from this graph, the one side limit, the whole limit, we may have the what we call the vertical asymptote, which is the x equal a. So what asymptote means? Asymptote means that if we have a curve and we say that we have asymptote, the curve itself will not be able to cross this line. Okay? Will not be able to even touch the line. Okay? But it will be, if you see here, when you try to getting close to A, the gap is closer, but it will never touch. Okay? Never touch the line, okay, from the curve. Okay? If you want to maybe this one. Okay, so from some functions that you can observe, sometimes you can figure whether the function has the asymptote or not. Okay? The idea is whenever it becomes like you have, for example, this part here, 1 over x squared, when x is 0, it becomes undefined, or it becomes a 1 divided by 0. It seems that it will going to reach some large number if we deal with the limit. So whenever you find a domain, okay, a domain that is making the functions undefined, okay, so you have some interval that make it undefined, and you check the other way around, and you will feel that it will be having some infinite. So probably you can test some numbers as well. Okay. So for example, let me go through the slide here. So if we check functions 2x over x minus 3. Of course, we can think on, first is the domain. Okay, the domain is supposed to be x is not equal to 3, so that it's not 0, right? So, because if 0 is undefined. So we can maybe make some assumptions that, oh, probably we have an asymptote. Okay. Now the other way, or the way to confirm, maybe checking some numbers. Maybe checking some numbers, x is, my suggestion is try to checking like 3.1 and x is 2.9. This is to check where the functions will, the direction of the function, whether it's going up or going down. Okay? Just to check the signs. Okay? So just some number, then you don't need to really calculate, just to see the signs, okay? Just to see the signs. So when we take the positive here, 0.1, it will be a positive, right? It will be a positive sign. So probably from the right side, when you move, it's going up. It's going up, okay? Or if you feel confused how this happened, perhaps we can check uh, the the numbers, maybe easy numbers that can be followed, and then checking this 2.9 and 3.1, okay? Checking the numbers that probably, if we see this is from the right, it seems f of x will be positive signs, right? And if we check from the left, that f of x seems going to be negative. Okay? So when we deal with the limit, if we want to check the limit, that's the limit as x approaching 3. Okay? How do we know? How do we know that we are true? So first is we can try to graph. Let me check my drawing. I think I don't have the drawing, so let me draw. And let's say this is x equal 3. So what is happening here is going to be that, okay. And the other one will be here. Well, probably it's not proportional, but suppose the illustration is correct. Okay? Or maybe we can check through our graph. Where is my graph? GOC. To x divide. Okay. Yeah, this is graph, and if we check the sorry, x equal 3. Yeah, this more reasonable. This is more reasonable. Okay. Then we can take this. Okay, this is, yeah, more better. And also you can check when x is getting larger, there will be different case. We call it limits at infinity, but we will talk later. You will see that it has another asymptote, the horizontal one. If you observe carefully, you will see that here is going to have another asymptote actually, but that will be another section, okay? Another topics. But just focus on the vertical asymptote. Okay? For this kind of functions, you can predict how the vertical asymptote can be in a function. Okay? Another function that is interesting is the ln. Okay? And also the tangent. That is very obvious for the asymptote. So if we have the limit as x approaching from the right, okay, this will be going to be, if you draw the ln, you will see that the function is only on the positive side because of the domain, of course. So we'll see here. Let me make a little bit bigger. So we see from this visuals, the ln is going to be negative to large if you approach from the right side to 0. And from the beginning of the limit introductions until now, we haven't yet discussed how to really compute the limit, as in with some math, right? So that will be the next topic. Okay, I think we can move on to. Oh yeah, since we are finished on chapter 1, right? The functions and some other important fundamentals. I think you need to prepare at least maybe next week. I will prepare a quiz for you for chapter 1. But that quiz will be, you don't need to like prepare in the class. I will just deliver by online, so you can just take your time doing it at your home. Not sure whether it will be 20 questions, probably 20, 15 to 20 questions. Okay. You can doing from your home. That's I will prepare some interval, like time interval, that you can choose which day you are going to do it. Every question has their own time limit. It will be different according to, well, it depends on the questions. Some question may be having 1 minute or 2 minutes for limit, or the other one that requires more calculation, maybe 5 to 15 minutes. Okay. Before some question that is just analytical, just looking at the graph, choosing which one is correct, maybe just 1 to 3 minutes that will be around, and some maybe 4 seconds, maybe 45 to 30 to 45, maybe for at least 45 seconds for some question that is really just looking at it and then you can, oh, this one. just a pick questions. Maybe next week I will announce later, and maybe next week not really in the middle of the week. Maybe not next week, but maybe around weekend, and then maybe several days after week. Okay. And also for the students who join online, you can also join the quiz. Just follow the updates on Moodle. Right. So the next part is the limit laws. I will just briefly show you several several computations. Suppose C is a constant and limit exists. Then if we have a two functions inside a limit, we can separate this. But remember, okay, the first assumption for all this that is happening is we need to have both limit exist. Okay. If I write with underline this positive here, this positive sign, it means that it also works for subtraction. Okay. So adding and subtractions usually they are works irreversibly. If you have a constant, you can factor out the constant. If you have multiplications, a product inside, we can also separate, becomes two limit. And if you have a quotient, we can also separate these two limits. And for quotient, we also need to define the denominator so that it's not 0. So it is not be 0. Okay, this is the standard limit law. There is another additional law for the exponent, the power law, the root law. Maybe I will write the next page. Let me write here. Okay. Let me move this a little bit up. Okay. So 5 is limit. We can power the whole limit, where n is positive integer. Integer is this. Okay. But I think you will confuse what is this. Let me just write integer. So if we have power, we can also have the root. Same thing. This will be the root for the limit itself. If n is even, then assume that limit is positive because of the square root, right? We cannot have negative if even. And of course, to apply all these things here, we need to also define that if we have a constant, this will be just a constant. Okay? And we have the just x, then it's going to be a. Okay. This is by definition, as it's obvious from intuitive definitions. Okay. And from there, we can have and also the n is positive integer. This is also n is positive integer. And if n even, a is positive. Okay. Okay, I will end up until here for today's class. We are going to review next week, and then how to evaluate the limit. Okay, before that, maybe any questions or something to discuss before we move to the evaluation. Okay, evaluation. Okay, any questions, guys? What is the password? That's the square root. Well, it still means simply substituting the a to the password. Okay. Any other questions? No? Okay, I think we can move to. Let me stop this. Wait. For a moment, let me share the screen. Okay. Okay. If you have trouble for scanning the QR code, you can just take the website and adding the code. Go to the website and enter the code. Okay, everyone, are you ready? Okay, let me start. Okay, let me start. Okay, use your student ID, okay, so that I can easily uh, adding your score in the system. Okay, get ready. Huh? Oh, the code. Wait. Okay, get ready. Get ready. You need to, I think, prepare some paper and pen or pencils. Yes. I just use the website, menti.com, the top one, menti.com, and then use the code 5 something there. You can go to the front, see the number if you cannot see from there. I think for this one you can also guess the number. If you're careful enough, you will find you will find when you guess the number. Okay, 3, 2, 1. Yes. Yeah, good, good. Like I said, you can guess the number, right? You can guess the number. Who's that? Okay. Okay, second one, get ready. Get ready. Okay, number 2. Just to check the logarithm. If we need to review, then maybe we can review it. Because we will deal with logarithm also in the, I think in the next few chapters, we'll also meet the logarithm again. Finish? So logarithm is asking the powers, right? Okay, so that's how it is. Okay. Okay, good. I think later I can review when we deal with another logarithm. Okay. And this is supposed to be you need to be familiar with. Okay. Okay. The next one, the last one. Okay. 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 Get ready. Last one. 3, 2, 1. Okay. Let's say this. I guess just to check. Just to check. I will explain if you don't really understand. I will explain next week. Okay. Just to check whether you know. Very fast. 33, 32. Okay, 6, 5. Okay, how many of you? Okay, it's true. Okay, it's true. Okay, because it's limit. Okay, because it's limit. Okay. Gonna see who is the winner for today's game. Oh, oh, oh okay, good, good. Okay, congratulations, congratulations, Peter. Okay, as usual, write your ID. Write your ID. This is for your attendance. And if you have suggestions, you can also write. You can submit multiple times. You can submit multiple times. If you have any request, anything to say, it's also okay for you. Okay. And this will be the end of our class. For online students, thank you for joining. You can also write the ID or ID in the system. Okay, any questions? Any questions? No? Okay, I think we can end the class. See you next week. See you next week. Okay, yeah, you're welcome, Andrew. Okay.